Alright, so we are looking at simplifying radical expressions. In order to start simplifying radical expressions, we are going to first review and look at our perfect squares. So when simplifying radical expressions, it's super important to know what the perfect squares are, because that's how we're going to simplify them. So, as part of the warm-up, it said, what are the first 15 perfect squares? So go ahead and fill in the top of all those boxes with the perfect squares. So again, that's like 1, 4, 9, 16, etc. Okay, so that's 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 196, and 225. So we have some new vocabulary. A radicand. A radicand is the monomial expression under the radical sign. A radicand is the monomial expression under the radical sign. So again, a radical sign is the square root. The reason it's called a radical and not a square root is because sometimes it can be a cube root or a fourth root, etc. The word simplify means to find another expression with the same value. It does not mean to find a decimal approximation. So for your homework tonight, I do not want any decimal answers. So tonight when you work on a homework assignment, you better not have any decimal answers, because that is not simplifying, that is approximating. The multiplication and division property of square roots says that if you have two numbers being multiplied together to make a new number under a square root, we can think of rewriting that square root as both of those numbers separated. So for example, the square root of 32 can be rewritten as the square root of 2 and the square root of 16. So we use the multiplication property oftentimes to help us rewrite expressions using a perfect square so that we can simplify with that perfect square. So we're going to be rewriting these expressions using perfect squares so we can simplify the expressions using those perfect squares. So we're always looking for the perfect square that goes into a problem. The division property is very similar to the multiplication. It says that if you have two things being divided, you can think of them as the division of the top over the division of the bottom. We're also going to talk about rationalizing. You cannot leave a square root in your denominator. So, for example, with this problem here, we'd have to go one step further, which is to take that denominator and to rationalize it. So we would multiply by the square root of 2 over the square root of 2, so that the square root of 49 became 7 square roots of 2. And then when you have two square roots multiplied by themselves that are identical, so like root 2 times root 2, root 4 times root 4, That's the same as having the square root of 4, or root 2 times root 2. So that becomes 2. So the square root of 49 over 2 is really 7 square roots of 2 over 2. So it's called rationalizing the denominator. You cannot leave a square root in our denominator. So you multiply by the square root of the denominator on top and bottom and simplify. Okay. So that's sort of a summary of where we are in terms of vocabulary. Now let's actually look at some simplifying problems. So the square root of 25. The square root of 25 consists of a perfect square. So the square root of a perfect square is that value. So you think of 25 as being the square root of 5 squared. So the square root and the square cancel, and you get 5. All perfect squares become their numbers squared, unsquared. 7 is a prime number. The square root of a prime number remains that square root. So if you get a prime number under your radical, it cannot be simplified. The square root of 7 is the square root of 7. And that's why I said I don't want a decimal. Like, I know you can type that on your calculator and get an approximation. We don't want approximations. We want actual answers. So we leave that as the square root of 7. Negative the square root of 144. The negative out in front does not affect my square root on the inside. So it's going to become negative, and then the square root of 144, well, that's really like 12 squared. So that's negative 12. Just like a single negative doesn't affect my answer, if you have a plus or minus in front of your square root, that also does not affect your answer. So this becomes plus or minus 3. Because the square root of 9 is 3, because 9 is a perfect square. So we get 3. Yes?
Could you simplify negative 144 more? Like negative 12?
That's what I wrote down.
I mean, could you simplify negative 12 more?
No. Because the square root is gone. So negative 12 is just a whole number at that point. So there's no more operations being done on it. Okay? And then for the next part, letter E, we have plus or minus the square root of 121. 121 is once again a perfect square. So this becomes plus or minus 11. That plus or minus really just signifies that I have 2 answers to that square root. It's like saying an answer is 11 or negative 11. So you have 2 answers when you have that plus or minus in front of your radical. Letter F, we have 25 over 81. So that's where the division property comes into play. You can think of that as the square root of 25 over the square root of 81, both of which are perfect squares. So you get 5 over 9. Okay, for the next one, you have the square root of 147. So again, it's easy sometimes to look for the perfect square that divides into a number. It's also easy to know our tricks that go along with numbers. So when I see 147, I know that this is divisible by 3, which is prime. So sometimes I look for the small primes that divide into it. I know this is divisible by 3 because of the dividing by 3 trick. So the trick for any number divisible by 3 is that you can sum all the digits of the number. So you would sum the digits of 147. So it'd be like 1 plus 4 plus 7, which is 12. If the number you get when you sum them together is divisible by 3, then that number is divisible by 3. So that's like a little trick to know if a number is divisible by 3. So like 25, for example, 2 plus 5 is 7. 7 doesn't divide by 3, so 25 doesn't divide by 3. 81 is 8 plus 1, which is 9. 9 divides by 3, therefore 81 is divisible by 3. So I'm going to use the multiplication property with 147 to rewrite that as the square root of 3. And 147 divided by 3 gets me the perfect square of 49. So again, I'm looking for a prime and a perfect square because that makes them easiest to simplify. The square root of 49 is 7. 3 is prime, so it doesn't simplify. You always write the whole number outside the square root first. So this becomes 7 square roots of 3. So the square root of 147 simplifies to 7 square roots of 3. The square root of 605, well, we know that anything that ends in 5 or 0 divides by 5. So once again, you could take 605 and divide it by 5. And you get 121. So 121 becomes 11, so you get 11 square roots of 5. If I'm going to divide by a number, I'm always looking for a prime. So like 2, 3, 5, 7. Dividing by 6 isn't a bad thing either because 6 doesn't simplify either. We aren't just simplifying numbers though, we're also going to simplify variables. So when we look at variable expressions and their simplifications, we have a pattern for simplifying these. So the square root of x stays the square root of x. If you have a square root of x squared, it becomes the absolute value of x. X cubed is really like x squared times the square root of x. So you get x square roots of x with no absolute value. The square root of x to the fourth is x squared. So in order to simplify, we're simply dividing the inside variable value by 2. Anytime you have an odd under your exponent, you will always have a square root in your answer still. So anytime I have an odd under my square root, I will always have a square root in my answer. And then there's a pattern among the evens. So there's also a pattern among the evens. Every time you have an even square root, like 6 and 2, and they simplify to an x value with an odd power, you need absolute values. So anytime I have an even inside, I take the square root, which is even, and my answer becomes odd, then my final answer needs absolute values around those variables. So I don't need absolute values on x to the fourth because x squared is even. The reason you need absolute values is think about the fact that any number squared is positive. So if I plugged in x equals -2, and I take the square root of -2 squared, if I were just to say that the square root and the squared canceled, I'd get -2. But we know that if I would square this, then take the square root, -2 squared would have become 4, and the square root of 4 would have become 2. So that's where the absolute values are coming into play when you simplify a variable. So if you simplify an even, and you get an odd value out, you need to have absolute values. As a general rule, you divide the exponent by 2. The remainder stays in the radical. So as a general rule for simplifying square roots, you are dividing the exponent by 2 and leaving the remainder in the radical. So for example, simplifying the square root of x to the 7th, that becomes 7 divided by 2, which is 6, and 1. 6 divided by 2 is 3, and then there's your remainder. So we have the square root of 12. This is like what we were looking at before. No variables, but we do know that 12 has a perfect square that goes into it. So we're going to rewrite 12 as the square root of 4 and the square root of 3, knowing that the square root of 4 becomes 2. Square roots of 3. The square root of 48 and x to the 6th. So we kind of simplify them separately. 48 is the same as 16 and 3. And then x to the 6th, well, 6 divided by 2 is 3. That's even though and becomes odd. So this becomes 4. Absolute value x cubed, square root 3. Only the x cubed goes in the absolute value because that's the only part that was odd. So 4 absolute value x cubed, square root 3. Okay, the square root of 400, x squared. So the square root of 400 is a perfect square. If you didn't know that and you broke it down into the square root of 4 and the square root of 100, that would still work because you would just take the square root of 4, which is 2, then 100, which is 10, and get 20. But if you recognize that the square root of 400 was a perfect square, and you just got 20 from the beginning, that's also fine. So sometimes when you're simplifying square roots, you may not see all of the perfect squares, simplify it all the way the first time. So it's important to know that you can simplify it all the way down the road. The second part is the square root of x squared. So square root of x squared is the absolute value of x. Yes. What? Yes. Yes.
For that, well, I was getting back a little bit. For that square root of x and 7, I was trying to write it down so I didn't have time to look at it. So you just take it out by 2.
Yes.
That could be x squared and then the square root of x.
So it's x cubed square root x. So basically what you do is you take that number and you divide it by 2. So like for the next example, we have x to the 5th. So since it's odd, it doesn't divide nicely by 2. So you write it as the even, 1 less than it. So x to the 5th is kind of like looking at x to the 4th and x. Now, even though it's odd, so if it's odd, you would never put an absolute value. So like with 7, it became x to the 6th and x. but we didn't put the absolute values on the x cubed because x to the 7 on the inside started odd. It's only if the inside starts even and becomes odd. And then 20, well 20 would become 5 and 4. I'm so sorry, I don't know why that board keeps glitching out. I think it might be the connection to the HDMI. So the square root of 5 doesn't simplify. The square root of 4 becomes 2. The square root of x to the 4th becomes x squared because you take 4 and divide it by 2. But then the primes, which are 5 and x, are going to stay inside the radical. Because you cannot simplify the square root of x and you cannot simplify the square root of 5. So 20 becomes 2x squared square root 5x. Okay, and then for the last part, so now we have multiple variables. That doesn't change your rule. So like the square root of 48 x squared y to the 4th, you take that multiplication property and you still apply it to each part. So we already know the square root of 48 is 16 and 3. And then x squared and x to the 4th are both, or y to the 4th are both even. So we divide their exponents by 2. So you get x and y squared. But because x squared became x, it gets an absolute value. And then for the last part, I simplify the square root of 16. So I have 4, absolute value x, y squared root 3. So the square root of 8, x to the 25. So 8 is the same as 4 and 2. And then 25 is really like simplifying x to the 24 and x. Because 24 is 1 less than 25. So you would divide 24 by 2 to get x to the 12. The square root of 4 is 2. So you get 2 x to the 12th on the outside, because those are all your perfect squares simplified. And the non-perfect primes inside, which are 2x. So it's 2x to the 12th square root 2x. Sometimes you get a perfect square with variables, and that variable is also a perfect square. So the square root of 9x to the 36 is considered a perfect square because the square root of 9 is 3. 36 is even, so you just divide that by 2 and you get x to the 18. Even becomes even, no absolute values needed. So the square root of 9x to the 36 is the same as 3x to the 18. So again, they're equivalent. If I plugged x in at the beginning or x in at my simplified form, it should be the same. So the last one, I have 6, x3, y6, z9. 6 only breaks down into 2 and 3. So it cannot be simplified. So the square root of 6 is staying in my radical. X cubed is like x squared and x. So an x comes out and an x stays in. Y to the 6th is even. 6 divided by 2 is 3. But we have an even becoming an odd, so it gets absolute values. And then z to the 9 is kind of like z to the 8 and z. So 8 divided by 2 is 4. So you get z to the 4th on the outside and a z on the inside. Everybody okay with that simplifying process? We start to see the pattern now. So you're looking for the even and then dividing by 2. And if you have an odd, you will always have 1 left on the inside. So what I want you to do for tomorrow is the front and the back of that simplifying radical expressions handout. So some have variables, some do not. On the back, I did put down the answers to the odds, but that means you need to have work. I put the answers on the back just to kind of give you an idea to make sure you're doing it right. So you might want to almost do the back before the front. The front also walks you through how to simplify and is an extension of our notes. So this is something I don't know the last time you actually simplified square roots, maybe algebra 1. So I want to make sure we're pretty good at it because we're going to do it a ton with the quadratic formula we're looking at next week. Yes? You can do 1 for both.